So, well, we are now, I mean, in this particular chapter of boiling and condensation. And yesterday's class, we have tried to understand what is this boiling and what is meant by condensation. Well, so we'll as per your as per the requirement of the syllabus, we'll have to go a little bit deep into this particular processes, that is boiling and condensation. That's what we are doing now. And yesterday, first we will talk a little bit more about this boiling, and then we will go a little bit deep in condensation as well. Well, yeah, this one that we had covered yesterday. It's an introduction to boiling and condensation, and we try to understand the difference between evaporation and boiling, and then yeah, then this is the one that is the boiling with flux from solid surface to the fluid is given like this, and where this delta Tx is nothing but the saturation the surface temperature minus saturation temperature. And also we discussed what is this saturation temperature. What do we mean by this saturation temperature? That also we discussed in the last class. Okay. With the help of T8, temperature enthalpy curve. Right. Now, today let us see the classification of this boiling. So boiling is can be classified into these two types of boiling. One is pool boiling, and the other is flow boiling. Okay. Now, well, the in pool boiling, there is no external force that causes the agitation in this particular type of pool boiling. I mean, there is no fluid. The fluid is not in motion. There is no motion in the fluid. It's stagnant. For example, while we make the tea, we put the water in a bowl and put it on a heater. Okay. So that's an example of this pool boiling. And then we heat. And we observe what happens to that particular water inside the bowl when we apply the heat. What happens? Ultimately, we find that all the water it will go on adding the heat, and all the water it evaporates and transforms into liquid to gases. Okay. Well, we know we know when we hit this thing that there is agitation between the particles of this water. That agitation gradually increases, and then so when we heat this one, the heat first of all the particles here, this particular heating process gets agitated, and then it strikes the other particles, and the process will content it gets agitated. So any motion of the fluid is due to the natural condition. Yeah, we know that is what it means by natural convection. Correct. And the motion of the bubbles under the influence of buoyancy. So what you will observe that how you can note these agitations in this particular water. you will see that a bubble formation takes place. First, you will see only a few, and then gradually these bubbles will increase, and then this first you will see that a bubble is formed near near the solid surface, and then gradually you will see the more bubbles are formed, and then at one point of time you will find that the complete content it's, it's full of bubbles and ultimately the transformation from liquid to gaseous state occurs. So that is why, and this bubble formation is due to the influence of buoyancy. Buoyancy effect is there. So any motion of the fluid is due to the natural convection of currents and the motion of the bubbles under the influence of buoyancy. Okay. And other one is flow boiling. What is this flow boiling? Flow boiling is called flow boiling in the presence of bulk fluid flow. That means there is a motion in this particular fluid. It is not stagnant as it was in the case of pool boiling. For example, water flowing through a pipe. Okay, so this is what happens here. So there is yeah, there is boiling is called a flowing in the presence of bulk fluid flow. So there is a fluid flow in the through the the container or say through the pipe here. Okay. So when there is this particular movement is there in the fluid, we call it flow boiling. Okay. So that's the difference between pool boiling and flow boiling. In flow boiling, the fluid is forced to move in a heated pipe. As you can see here, all the heat rays from all sides. Heating is done, forced to flow through this particular pipe. And how? By means of some external devices such as pump, you can say, pump through this particular pipe, which is heated, already heated. So, what we conclude now? That two types of boiling possible. One is pool boiling and the other is flow boiling. Pool boiling, every day, you will find it in more in use, more number of uses, rather use of flow boiling is also there are plenty of applications are there. But more often you will see for our household work and all these things, you will see this pool boiling process. So another two type of boiling also is considered apart from that flow, a pool and flow. This is they are called sub-cooled boiling and saturated boiling. Now see what is this sub-cooled boiling? You see here, this one heating is taking place. Well, this is a this classification is basically of the pool boiling. As you can see, the boiling of the previous one that we divided into two categories, pool and flow. And now this pool, under this pool, we can have these two, subcooled and as well as saturated boiling. What happens in the subcooled boiling? When the temperature of the main body of the liquid is below the saturation temperature. So, when you uh, heat, say our at this particular heating surface, we have a temperature of 170 degrees. Now, if the water is in room temperature, then what will happen? Gradually, it will try to accept the heat, and thereby its temperature will increase. Now, what is this subcooled? When the temperature is below the saturation temperature. So this is, as you can see here, water. We know that for water at 1 atmospheric pressure, the saturation temperature is 100 degrees Celsius. So when this is you know, less than that saturation temperature, then also this boiling will take place, and that we call sub-full boiling. And just observe this, the position of the bubbles, the number of bubbles that you can see. So this is the nature that you get when the temperature is below of the liquid, in this case it is water, is less than the saturation temperature. And when this temperature reaches to this height, this saturation temperature, in this particular case, this is 100 degrees Celsius, then that is the saturated boiling. So when the temperature of the liquid is equal to the saturation temperature, then we attain this saturation boiling. And also, just see now the bubble positions. Look at the bubble positions in this particular bubble. So, full boiling, flow boiling, then full boiling, further classified as full boiling and saturated boiling. Okay. Okay, now if I go there, this classification, two type of classification. One is classification of boiling on the basis of presence of bulk fluid motion. So this one, when there is no motion, there is in one case there is no motion, and in case there is motion. So this classification is based on the fluid flow, pool and flow, and this is basically this one. Though this is a part of, we have discussed as a part of pool boiling, but this is actually the classification of boiling on the basis of presence of bulk liquid temperatures, on the basis of the liquid temperature. Okay. Now we'll go a little bit deeper now to understand this pool boiling. Again, let us see. Consider a familiar example of water around 20 degrees Celsius taken in a pan or stove. Fine. Initially, when heat is supplied, small bubbles are observed on the pan. What I say? These are the air molecules dissolved in water. Bubbles are nothing but air molecules dissolved in water. This should not be confused with vapor bubbles. Yeah, right? With further heat supply, chunk of liquid starts rolling up and down by natural convection current. This is followed by vapor bubbles near the bottom surface of the pan. These bubbles detach from the surface and start rising in the water and collapse without reaching liquid surface. Before it reaches the liquid surface, the bubble collapse. That means you will find that bubble gets just like there's a loses its existence there. It means it becomes, the bubble collapses and it mixes with the liquid. This is sub-cold boiling, wherein the liquid has not reached the saturation temperature. What we discussed. With further supply of heat, the intensity of bubble formation increases, rises and reaches liquid surface. Now the bubble has reached the liquid surface. When the water temperature reaches saturation temperature, this full-scale boiling is known as saturated. Okay? Fine. Let's go to the next. Now, you see here, the process of boiling depends on nature of surface. You see, the boiling depends on, this one I explained yesterday also, on the surface, thermophysical properties of the fluid, and vapor bubble dynamics. From these three, this process of boiling, it depends. Okay. Now, the electrically, see, this is a wire submerged in pool of water at certain temperature and varying the wire surface different. Now, when this pool boiling occurs, then uh, with respect to this heat flux and the excess temperature, which is nothing but the actual temperature minus the saturation temperature. We'll see it in a little bit detail now. So on this basis, whole process from liquid to the vapor, you can divide this whole process into three divisions, three regimes, regions or regimes. First one is interface evaporation or free convection up to certain temperature difference. And then we have nucleate boiling here, this region, and then we have film boiling here. Okay, we will talk about the individual regime now. So let us, okay, we will come back to this one. Right. This pool boiling, we will see the different regimes now. Okay, as we have seen in the previous diagram. In pool boiling, okay, I'm not going on detail, this also. Now, what is this boiling? Heat flux and boiling is H specifically into Ts minus T saturation. And this is known as T excess, means temperature excess of saturation point. Only then the gaseous, the liquid will convert into gaseous form. So boiling takes different form depending on this temperature difference or the T excess over the saturated temperature, different regimes were defined that we have seen in the last slide. Now, well, this is what we saw in the previous slide. So, natural convection zone, nucleate boiling, transition boiling. Yeah, we can see one more part here. In the previous slide, it was a general one. So let me show you. So we consider this thing. This is the transition part, as you can see here. So nucleate in the next one, we have divided this film boiling into two parts: transient and then film boiling. But for our discussion, individual discussion. So we term it as transition boiling and we term this as a film boiling. Now we will see each and every one separately, these regimes. Okay. Now what is there? And along the y-axis, heat flux boiling, we have put, and here the t-axis, that is the excess temperature of above the saturation temperature. Okay. Now we can see that this is a 1 to 5 for this particular. What we have taken here again? We have taken water again for our discussion. Now you can see here, from here to here, the curve looks like this. As the heat flux, with the increase of heat flux, we get a curve like this. Now what happens here actually? How do we have defined this particular regime? Let's see now. This is natural boiling, right? Yeah. So that's the same figure is here. So this is from point A to point A on the boiling curve. Yeah, this is the point A. So from here to A, this is the natural convection zone, boiling zone, right? What happens here? What happens here? Here, bubbles do not form on the heating surface until the liquid is heated a few degrees above the saturation temperature. So to form bubble, the temperature should be increased up to some more than the saturation temperature. Only then the bubble forms. That means the liquid is slightly superheated in this case. Okay. The fluid motion in this mode of boiling is governed by natural convection current. Simple, as we had discussed earlier. Here, you see, we have the bubble here. The surface temperature, as you can see, this is what's that? Yeah, you can see the surface temperature here. I think it is 105 degrees Celsius, and this is now what happens here. It is within that the saturation temperature. It has not crossed the saturation temperature. So in such case, what happens? You will see. You can try it out at your home. Just try to heat some water. You'll see that immediately the bubble formation doesn't take place, right? But water gets heated. But immediately the bubble formation doesn't take place. To form a bubble, that temperature has to rise beyond the saturation point. Now, till such period, such time that no bubble is formed, we term this zone as a natural convection boiling. We term this boiling as a natural convection boiling. So this is the zone which is, we call it natural convection boiling. Okay, and here, of course, yes, it is the heat transfer is by natural convection. Okay. Now, for the conditions, natural convection boiling ends at an excess temperature of about 5. So, after that, that natural convection is, there is no longer the natural convection takes place. And means in this particular, for here up to this 5 degree difference, after this, there will be no natural convection mode of heat transfer will take place in this particular water. So, this is the zone that natural convection boiling regime. That's the where there is no bubble formation is there, but till such time. Then comes the next one, nucleate boiling, and that's between A and C. You can see here also, yeah, that is between point A, point A to C. This portion is, so you can see we have divided into two parts. One is the temperature difference of 10, and the other is from 5 to 10, and the other is from 10 to 30. 10 to 30 difference. Now you see what happens here. What happens here now? The process. In this particular zone, as you can see here, the bubbles collapse in the liquid. Bubble collapse in the liquid. Bubble is formed, but it collapses within that particular, in the liquid itself. From 5 to 10. That is from point A to point B. Okay. So let's go back to the narration. Bubble forms at an increasing rate. Formation of bubble starts at an increasing number of nucleation sites as we move along the boiling curve towards the point C. तो यहाँ से यहाँ जो हम जा रहे हैं, this bubble formation starts increasing. Okay, and region A to B, isolated bubbles, just formation of bubbles takes place in this A to B, and the bubbles they collapse within that particular within the liquid from this to this, and this is for this particular water under consideration, 5 degrees centigrade. Okay, that is Txs is between 5 to 10 degrees. So in this region, this happens. Bubble is forming and it is collapsing in the liquid again. So that is what is happening. Now, when we cause this particular temperature difference, then more number of bubbles starts forming. More number of continuous column of bubbles you can see, and continuous column of vapor in the liquid. So what happens in this particular portion, 10 to 30? Well, the bubble reaches the surface, and then the vapor starts forming. Let's see here. So what is happening here? These bubbles rise to the free surface. That is, comes to the surface. And what is happening? The bubbles from here, from the bottom, moves upward. This particular reaches the surface, and then it turns into gases. So bubbles rise to the free surface. God, it is rising to this particular surface here. In this nucleate zone. Yeah. The point A is referred to as onset of nucleate boiling. Point A, the starting of this nucleate boiling, we call it onset of nucleate boiling, or in abbreviation ONB. Goes there, and now the vapor has started forming here at this point. Vapor start forming. Now there is a next, let us go to the next regime. Yeah. Some little bit more clarification on this particular regime. Region AB, the stirring and agitation caused by the entrainment of the liquid to the heater surface is primarily responsible for the heat transfer process. Now, there's a large heat fluxes obtained in this region are caused by the combined effect of liquid and entrainment and evaporation. Well, we have discussed all these things. It is certain more explanation on that. Now let us see. You see here from A to B, after the point B, the heat flux increases at a lower rate. Well, heat flux, if you see the curve, nature of the curve, you will find that the heat flux increases at a lower rate. The heat flux is now it is increasing. As you can see, the heat flux is increasing all the time. So that heat flux is, but the rate is lower after this point B. Okay, and reaches the maximum. After that, you will see that heat flux reaches this particular point. That is C. It reaches a maximum point. Let me go to the original drawing here. What is happening here? From here, the heat flux, as you can see here, you see the nature of the curve. There is a difference between these two. The rate at which this the flux, heat flux in the regime from A to B, and this one is lower than this particular one. And ultimately, a point is reached, this particular C is reached, where the maximum heat flux occurs. Maximum heat flux occurs. That means, what is this C point? Now here, the vapor formation starts. Now, if you heat further, what will happen? The heat flux will not get changed now based on this point. And this is known as maximum critical heat flux, Qmax. So, it reaches the maximum at point C. The heat flux at this point is called the critical or maximum heat flux and is of prime engineering importance. So this is now the zone has come which will be utilized for engineering purpose. Okay, beyond this, now the vapor is generated. Now we can use this particular vapor. Now, okay, transition. Transition, as you can see, next zone is, we call it transition zone. Now here, the temperature, excess temperature is increased past point C. See, it has increased considerably from this one. Shall I go back here? Yeah. Now you see here, this transition zone. Now the difference is from 32. This is temperature difference is from 30 to 120. So this. And what happens actually here, for your understanding, you can see see the bubbles here. And now it is increased when we are increasing this excess temperature T excess further beyond this particular point C. What happens? The heat flux decreases. So now this flux was increasing, and after reaching the critical point, as the temperature difference is increased, we start getting the heat flux starts decreasing. And we can see here starts decreasing now. This is because the large fraction of the heating surface is covered by vapor phase. Now, this is because the vapor has already been generated. Okay. Now, this particular zone, if you see this part and if you divide it into a right and left part, you will find that there is a mix of the regimes. You will find that inside, as you can say, in the transition boiling regime, both nucleus and field boiling partially occur. So in this particular, that is why this zone has been mentioned as transient boiling. So here you will find that both sides, in some towards this side, you may find the nucleate boiling, and in this part you will find the, and this process goes on. Okay. And also this zone is known as unstable film boiling rate. It's transient zone. Okay. And this occurs from for water. It happens from 50 degrees temperature difference of 30 to 120 degrees. Okay. Now, next comes the film boiling beyond point D. Now, beyond point D, what is happening? Let us see. Beyond point D, the heated surface is completely covered by continuous. Now, total vapor formation has taken place. Total vapor formation. Okay, total vapor formation has occurred now. Phase change has completed. Now from D, where the heat flux reaches a minimum is called the leaden frost point. So this particular point where the heat flux reaches the lowest value is known as this one, known as leaden frost point. Leaden frost point. Okay, and yeah, leaden frost point. The presence of a vapor film between the heated surface and the liquid is responsible for the low heat transfer. Now the heat rate increases with increasing, and now you can see that the heat flux is again increasing. Okay, and as the temperature is our temperature difference is increased. Okay. Now, actually, what happens from this 11 point, 11 first point, process is now evaporate and radiation. So, this is now the process is the heat transfer is by the radiation. Okay. Well, now there is another one, burnt out phenomenon. What does it mean? See, a typical boiling curve does not follow the boiling curve beyond point C. Up to C, all of this follow this one. Follow this curve of this typical boiling curve of this boiling curve. Now, what happens here? You will find when the power applied to the heated surface exceeds the value point C, slightly the surface temperature increases suddenly to point T. Now, what happens here, when it reaches here, actually, so suddenly you will see there is a jump of temperature of this, which actually it should have come like that over this temperature difference. But from this one, you will find that there is a sudden jump to this particular point E. Okay. Now, when the power is reduced, gradually starting from again when well this is with respect to power reducement. If you are using an electrical device, if you increase the power, then the process becomes like that, and you can decrease the power also. So on that basis only it has been mentioned as the power applied to the heated surface. When the power is reduced gradually, starting from V, the cooling curve follows figure this. So again, when the power is reduced, you can see that cooling curve, this curve follows like this. Again, it drops up to this point, mm, this, and then ultimately it comes like this. So this is this particular phenomenon that occurs. We call it burnt out phenomenon. Now we'll summarize this one. Yeah. So this is about the first one, that interface evaporation or free convection. This occurs in the region 1 called free convection zone, where 5 degree. In this region, the liquid near the heated surface is superheated slightly, and subsequently elevation occurs in the liquid with no bubble formation. Okay. Nuclear boiling, 2 and 3 phase. Mm, well, yeah, this is, they have divided in this way, 2 and 3. Okay. So nuclear boiling, this type of boiling occurs in region 2 and 3. In the region 2, bubbles begin to form on the surface of the well and dissipate to the liquid at the breaking away of the water. Okay, fine. With further increase of temperature, bubbles form more rapidly at nucleation sites and forms numerous columns of vapor way up to the liquid surface. Well, we know that. Okay, now the vapor formation starts. And nuclear boiling, exist up to 50 degrees Celsius. And then critical heat flux or burnt out point. The maximum heat flux, known as critical heat flux, occurs at point A on the boiling curve. In this particular curve, it is A. In our previous case, it was C, right? So point A on the boiling curve, at which transition from liquid boiling to thin boiling and is of the order of 12. This is the for this particular water. Beyond this point, boiling process becomes unstable and the temperature will be far higher such that metal surface get damaged or it may even melt. Okay, and that is why this heating equipment is operated with this rate. So this is what the burnt out point. This is beyond this one, suddenly it can, as you can see here, suddenly it can become unstable. So you can get between here. Well, so this is about the different processes. Now before I end this okay particular class, I will show you this a small video now to understand this thing, this particular whole process of what we discussed just now. So let me start the video. Yeah.
We can play some video for better understanding.
Is it audible?
Yes,
Was
sir.
it audible? Okay.
Yes, sir.
Okay.
With respect to the heating surface, to understand this point, let's consider an example of a vessel containing some water placed on a burner. As the heat gets transferred from the bottom surface of the vessel to the stationary water, it starts rolling up and down. Then bubble formation takes place. And after some time the water gets boiled. This process is a pool boiling process. Pool boiling takes place in different stages. They are pre-convection boiling, nucleate boiling, transition boiling, and film boiling. These different stages can be easily plotted on a heat flux temperature plot. X-axis represents the difference between the current temperature and saturation temperature of water, which is represented by delta T excess. And y-axis represents the heat transfer to the water per unit surface area of the vessel, which is represented by heat flux Q dot boiling. The curve OABCDE is known as the pool boiling curve of water. Here, curve OA represents the stage pre-convection boiling. Curve ABC represents the stage nucleate boiling. Curve C represents the stage transition boiling. And curve D represents the stage film boiling. Now let's understand each section of the curve one by one. Let's discuss about curve OA represents the stage pre-convection boiling. When we light the burner, heat transfer takes place between the vessel and water due to free or natural convection. We can see that the values of heat flux and delta T excess start increasing. And when the temperature of water reaches its saturation temperature, that is when delta T excess attains a positive value. Then boiling takes place. This stage of boiling is known as pre-convection understand liquid entrainment. Due to continuous heating, we see that the value of delta T excess increases, and the bubbles are formed at the bottom surface of the vessel. These bubbles move upwards and carry some water along with them, but they collapse after covering some distance in the water. This is known as liquid entrainment. We see that the disturbance caused by liquid entrainment in the water increases the heat transfer coefficient, so the heat flux also increases. In curve BC, we see that as delta T excess further increases, the bubbles start forming at a faster rate. These vapor bubbles move upwards and merge to form numerous continuous columns of vapor in the liquid. The bubbles in the column then move upwards to the free surface, where they break up and release their vapor contents. Due to this, the heat flux attains its maximum value, known as critical heat flux. Thus, the complete stage of boiling from A to C is known as nucleate boiling. Curve C represents transition boiling. As the vapor of delta T excess increases beyond the critical point, we see that the heat flux starts decreasing. This is because a large fraction of the heated surface of the vessel is covered with a vapor film. This vapor film acts as an insulator as its thermal conductivity is lower than that of water. Thus, the value of heat flux attains its minimum value. Point D corresponding to the minimum value of heat flux is known as line frost point. In curve C, both nucleate and film boiling takes place partially. Thus, this stage is known as transition boiling. Curve D represents the stage film boiling. We see that after the transition phase, the delta T excess further increases, due to which the vessel surface is completely covered by a continuous stable vapor film. Now, because of high temperature, we see that the radiation heat transfer takes place between the heated surface and the water through the vapor film. Thus, this stage is known as film boiling.
Okay, so this was the film which summarizes whatever we have discussed today. Okay, so let us conclude the session for today here. Please put on your videos, please.